Section 6.2, volumes. This is actually one of two sections where we will be looking at volumes. This first section, there's two methods for how we will find volumes, and then in the next section, there will be a third method that we'll see from that. The idea of volume follows from what we've learned about area. To find the volume of a solid, like a rectangular prism or a circular cylinder, you can find the area of the base and multiply by the height. So a rectangular prism, just think like a cube, but it doesn't have to be the same length of sides on all sides. So there's like a rectangular prism. You would have a base. You could find its area, and then you could multiply it by the height, and that gives you the volume. A circular cylinder, just think of like a can of Pepsi. All right, you've got a circle on top and bottom. That's a circular cylinder. Same idea. You can find the area of a base, which is really just a circle, and then multiply by the height. In the same regard, if you turn the cylinder or prism on their side, you can multiply the base area by the depth or the thickness. So what I mean by that is if we take this cylinder and instead of drawing it the way that I just did there, what if it was like this? It's just laying on its side. So imagine you've spilled the can. You can still find the volume in the same way by taking the base area again, which is still just a circle, and then multiplying by the depth. In this case, instead of height, now you have like a thickness of it, which you can also think of as depth. We're just playing around with dimensions and how you can perceive things. This is how we can find volume using calculus, what I've done here with the cylinder. We're going to start orientating things this way to try to find the volume. Also, if the solid figure is not uniform in shape, then you can find volume by using areas of cross sections and multiply by the related thickness. So imagine doing that with the following images. So first of all, what do I mean by something that's uniform or not uniform? This cylinder over here, this is uniform in shape. You have the same size throughout. Same idea with the prism, that is uniform in shape. But what if we had something a little bit different? Like this. And then maybe we imagined that it was three-dimensional. So you kind of have to imagine that it's three-dimensional in the page. The idea of not uniform is I've got this waviness that's going throughout my shape. Okay, but what we can do is maybe cut this into cross sections. So what if I just cut it and then got this sort of cross section here? It could be some sort of circular shape like that, but that would be different from if I did a cross section somewhere else on the shape. The idea is each cross section has its own base area, and then you can multiply by a particular thickness. So if you maybe had like some thick piece there and you just sliced it off, you could find the volume of that part. And then you could do the same thing with somewhere else in the image. So the idea of thickness is just how thick maybe this section would be. And then for these cross sections, we again have this idea of a base area. So, using some language that we've seen before, if we take some complicated figure like I've just drawn and cut it into cross sections, if the ith slab, which means first slab, second slab, third slab, fourth slab, etc., ith, any one of them, has a depth or thickness of delta x and a base area of capital A for area of x sub I star, then the volume of the ith slab, which we can call that ith slab as S sub I, is V of S sub I, so volume of that ith slab is equal to, take the area of the cross section and multiply by the thickness. Same idea as we have with the cylinder. You could take the area of the base area of the circle and multiply by the thickness or the depth. but now you can do this with other images. And in fact, if you think about what I've drawn here on the left, technically this is really a cylinder that we're looking at, just on its side. It's just that its thickness is maybe not as wide as the can. If you've ever sliced pepperoni before making a pizza, that's the same idea here. So by the same logic that we've seen in chapter 5, the total volume can then be defined using an integral. If we have the volume of just one slab, well, how many slabs do we have? We have from 1 to n as n goes to infinity. So we are adding infinite numbers of cross sections to give us the whole volume. So let capital S be a solid that lies between x equal a and x equal b. If the cross-sectional area of S in the plane P sub x, which is through x and perpendicular to the x-axis, if that cross-sectional area is capital A of x, where a is a continuous function, then the volume of that solid, capital S, is V for volume, equal the limit as n goes to infinity of the sum from I equal 1 to n of capital A of x sub I star, so the area of that ith slab, times delta x, the thickness of the slab. You add up all of those cross-sectional small volumes, and you get the whole volume. And really, that's just the integral from a to b of capital A of x dx. Notice that by this definition, the cross-sections are obtained by slicing through a value x on the x-axis, which makes the slices perpendicular to the x-axis. You could also do the same thing slicing perpendicular to the y-axis and integrate with respect to y, if that is easier for a certain problem. To see what I mean by that, again, if we go back up to this image that I have up here, what if the horizontal axis just ran through this image? Then I'm slicing perpendicular to that axis. That's where those little red slices are coming from. But if you think of the cylinder that we started with, it might make more sense to think that a vertical axis is going through that. So we will see some examples where we have either or, just to see the differences between those. So let's start with this example. Show that the volume of a sphere of a radius r is capital V equal 4/3 pi r cubed. So this is actually a known formula, the volume for a sphere with radius r, but now we're going to actually prove that this is true. So to do this, imagine placing the sphere so the center is at the origin. So if you want, you can start with a sphere, which if you've ever wondered how to draw a sphere, I'm not an incredible artist by any means. I just draw a circle and then I just show that it has some sort of dimension to it. All right, that's my sphere. Imagine that that is at the origin. So you can think that the origin is at the center of the sphere. You can think that you've got your vertical and horizontal axis. If you're thinking three-dimensionally, then you've got something like this. The line from the origin to the edge of the sphere has length r. That's what it means to have a radius of r. So from the origin out to the edge of the sphere, that's r. We can write the y-coordinate for any point on the sphere in this way. Y equal the square root of the quantity r squared minus x squared. So what I mean by that is if you have your axes like this, even if they are three-dimensional, you could label something like we've done, y and x, and we could say that the z-axis is out here. And we could find the y-coordinate of a particular point on the sphere by just using an image that we start to see take shape here. And what we're actually going to do now is, I don't even need the sphere to consider this. So, how about we draw a new picture where I just think, okay, maybe a cross-section of the sphere that I can imagine looking at. Let's say this is R, and I'm going to have negative r out towards the left. There's my x and y axis. I'm also going to have r up here on the vertical axis. And I'm just going to imagine the same picture that I have on the left, but I'm just going to look at a semicircle. So there, it's like I just took this part of the sphere. I don't need the whole three-dimensional part, and I don't even need the bottom part. I'm just going to consider one piece of it. And now, what I was saying earlier is the distance from the center to the edge of the sphere, that's radius r. And then they're asking us to describe the y-coordinate for any point on the sphere, which I could use this picture and say, okay, here's a point on the sphere. I want to know what its y-coordinate is. So to find that, we're going to use a triangle. And in fact, a right triangle. And we know some things about this triangle. The hypotenuse is r. And if I want to find out what the y value is, I can use the x-coordinate. For any point x on the x-axis, I can use that to find the related y-coordinate. So just from my triangle there, I have x squared plus y squared equals r squared, which means that y squared is equal to r squared minus x squared, which means that y is the square root of r squared minus x squared. If you needed a negative y value, like what if I looked at the bottom semicircle from this? Well, then obviously that's the negative square root. But we have a general way of finding those y-coordinates. Okay, so now that we know where this came from, let's move on to the next part. If we slice perpendicular to the x-axis, we get another circle. So let's actually think about this picture that I have on the right there. If I was to cut through the related sphere right here, that would be like if I cut through back on the original graph. And again, imagine you're cutting through with like a knife. If you've ever cut an orange in half, what do you get? You look at two faces that are circles. So the same thing happens if you cut towards the edges. You're going to get some circles. So that would be like a circular shape that you've just sliced off. So that circular shape, notice it has a center that's at the x-axis. And then the radius of that new circle is just the distance from the x-axis to that point that has a y-coordinate of what we've said y is square root of r squared minus x squared. So this circle that I have here, you've got the center is the x-axis, and you've got the distance from the x-axis to the top of that circle. That's that y value that we just described. Okay, while you're doing this, you do definitely want to try to imagine some of these shapes in your mind and even just do some rough sketches like this just to think of what it might look like. But if you imagine a shape like a piece of fruit that you've probably sliced many times before, when you slice through it, you're cutting it with a knife, which is a two-dimensional shape. You are then creating some two-dimensional shapes on those cuts. And on a sphere, that would be a circle. So now, what we have, when we slice perpendicular to the x-axis, we get a circle. And that circle has radius equal to y equal to square root of r squared minus x squared. Notice that this y value changes as x ranges from negative r to r. In fact, what if you were to slice this sphere right here at the outer edge? You would essentially just be running the knife tangent to that sphere. And so you wouldn't get a circle. In fact, the height of that radius, the height of that circle that you would get would have a radius of 0, so that would be nothing. Which should make sense if you think, if I plug r in for x, then I would have square root of r squared minus r squared, which is 0. You get the same thing if x is negative r. So if you think about that, then that's telling you that x is ranging from negative r to r, because that's how wide the sphere is anyways. So the area of one of those circular cross sections created after slicing is the area of the circle, which means capital A of x for our purposes will be pi times the quantity square root of r squared minus x squared squared. And when you square a square root, that leaves you with A of x is just pi times r squared minus x squared. If we integrate from x equal negative r to x equal r, we will get the total of all of those areas, meaning we can just think that we're going to be getting circular cross sections throughout, and then we're just going to be adding them up. So our volume is just the integral from negative r to r of pi times r squared minus x squared dx. So I'm integrating with respect to x. Pi is just a constant, so it's just going to be the constant that's multiplied by the antiderivatives. The antiderivative of r squared, remember r is the radius, it's also a constant, so the antiderivative is that same constant r squared times the independent variable x. And then the antiderivative of x squared is x cubed over 3. And then I'm just going to be evaluating this at r and then negative r. So plugging in r first, I would get r squared times r, that's r cubed, minus r cubed over 3, minus, and then parentheses, plugging in negative r squared times negative r is negative r cubed, and then minus negative r cubed, that would turn into plus r cubed over 3. And so then just replacing the negative inside the parentheses by distribution, I can see that I am going to have 2r cubed and then minus 2/3 r cubed over 3, or sorry, minus 2/3 r cubed. So 2 minus 2/3, that's 6/3 minus 2/3, that's 4/3. And so we do get 4/3 times pi times r cubed. All right, so that's one use of this volume integral that we've come up with. Now we're going to start to see some variations on this by thinking of how we did this problem by just imagining a curve that was above the x-axis, and then thinking that we could use that curve to find a three-dimensional shape. That first example that we just did is also an example of what is called the disk method. When I was doing that example, I was thinking of these cross sections, and when I did that, I'm getting things that look like disks or coins. We can use those disks and then add them all up to find a volume. And in those disks, the area of a cross section just has an area that is pi times radius squared, where the radius is simply the distance from the x-axis to the top of a curve. That is what I was demonstrating with this circle over here. The x-axis was really coming out of the screen towards you from this black point. And then the distance to the curve is that y value that we were talking about. This can be extended to any function, not just the simple function of a semicircle that we had in that previous example. So here's another example that has a similar setup, but also uses some logic from section 6.1, which was the section on the areas between curves. I'm taking this example from the homework, and this is from the section that is called Determining Volumes Using What's Called the Washer Method. A washer is essentially a disk with a hollow center. So, if the cross-section is a washer, then the area of the cross-section will be similar to what we talked about with the disk method. It will involve two areas of circles and the difference of them. So, if I have a disc, I can create a washer by just cutting a hole out of the center. And if I wanted to find the area of what's left after cutting the hole out of the center, you can think that all I need to do is just take the area of the circle that has the larger radius and subtract the circle that has the smaller radius. So instead of saying larger and smaller, we're using outer radius and inner radius. So the area of a washer is pi times outer radius squared minus pi times inner radius squared. So here's the question that comes from that section. Define capital R as the region bounded by the functions f of x equal to x plus 1 and g of x equal to 2 between x equal 1 and x equal 4. Choose the integral below that describes the volume of the solid created by rotating R around the line y equal negative 1. So this one example will show us a general theme of creating three-dimensional figures by rotating a region around an axis, which is actually a lot of the volume questions you're going to see throughout this section and the next. So first, I'm going to start by just graphing the region capital R that they've described. We're given two functions, f of x equal x plus 1 and g of x equal 2. You can write those using function notation. Sometimes I find it easier just to think of these things as y as a function of x or x as a function of y. So y equal x plus 1, that's a line, and it has a y-intercept of 1 and a slope of 1. So I'm just going to sketch a line that shows that. Y-intercept of 1, slope of 1 over 1. So I get another point at 1 comma 2, and then I can just draw a line connecting those points. And then y equal 2, that's a horizontal line with a y-intercept of 2. So this is my line y equal 2. And now I also want to focus on when they said we need this where x is between 1 and 4. So I'm going to focus on, here's x equal 1, there's x equal 4. So it's like I'm now seeing the region that's taking shape. It's this region here. That's the region R. All right, so now we've got our region R. It's bounded by the functions that we were given and the x values. And I want to take that region and rotate it around the line y equal negative 1. The line y equal negative 1 would be down here. So this becomes actually what we call the axis of rotation. The axis of rotation is y equal to negative 1. So I'm going to actually go back to my picture now and remove some of the things that I've marked so we have a little bit of some room to visualize some things. So I'm going to take away the dashed lines because I know where the region is. And I don't really need that part of the line there or that part. I don't need my descriptions. Just need some sort of clear picture to imagine what this region is going to do. So my axis of rotation is y equal to negative 1. So now if you turn your head maybe to the left or the right, imagine rotating this red triangle around this axis. And when you rotate things, you're creating circular shapes. So for example, if I started on this lower point on the bottom left of that triangle, and I rotated it around that line y equal negative 1, I would get some circular shape like that. Do you think I would get the same circular shape if I started with the point on the top right? that's farther away from this axis of rotation. So I'd get a circle, but it would be bigger than the one that I just visualized with the other point. So we can just over accentuate that. And you can kind of start to imagine what's taking shape here. If you did that with all of the points in between, you're creating kind of like a cone, or maybe like a coffee filter, because it's got openings on both ends. Spoiler alert, usually when I try to visualize things with calculus, it always devolves back to something involving food. I don't know. It's just an easy way to think of things. So you've got this sort of cone shape here. All right, and it's got a hollow center to it, because you can see that I'm just rotating around the axis. None of my region is touching the actual axis of rotation. So I'm going to have this hollow center to it. If you maybe turn this, on its biggest circle as the bottom, that might give you an indication of what this would look like. All right, so now let's see how the words that we had get used here. Outer radius and inner radius. Outer radius would be from our shape, the furthest point on the shape. How far is that to the axis of rotation? So there's my outer radius. And what we can notice is that's going to change, right? The outer radius on the point that's on the lower left part of the triangle compared to the outer radius as you keep moving along that green line, it changes. So this outer radius is not constant. It's going to keep changing. You could do that with different lines to help you visualize the outer radius. You can see that it changes as we move around on that green line. So how could we figure out what that outer radius is equal to? It has to be a function. Very easy. Just think that you are taking a y value that's on the line and you are subtracting a y value that's on the axis. How do I know that I'm subtracting two y values? Because this is a vertical line. So for the outer radius, as you're trying to get used to this, something that you could use to help, if your axis is horizontal axis, the outer radius and inner radius will be differences of y values. So for example, my outer radius here, in this example, it's the y value for a point that's on the green line. And what are those y values? They're given by the equation. Y is equal to x plus 1. And then I have to subtract y values that are on the axis of rotation. But what is any y value equal to on this axis? -1. Now I'm sort of abusing notation here by writing y equal x plus 1 minus y equal -1. That's because I'm trying to get you used to this. You're subtracting y values. But really, what is it? It's the y values that come from x plus 1 minus the y values that come from -1. Which means the outer radius is just x plus 1 plus another 1. So it's just x plus 2. Can we do the same thing with the inner radius? Inner radius. How would we find that? Well, that has to come from the function related to the blue line. So my inner radius is how far is it from the blue line to the axis of rotation. Does that change? No. In fact, it stays the same all the time. Just because of this particular example. That blue line had a constant related to it. But I can find it conceptually the same way. It's the y values that come from the blue line, y equal 2, minus the y values that come from the axis of rotation. So this is really just 2 minus negative 1, which is the same thing as 2 plus 1, which is 3. So now I have my outer radius and my inner radius. So to find my volume, I know I'm just going to use an integral with my area, and then my limits of integration, those are just what they've already stated. X is between 1 and 4. So putting this all together, the volume is equal to the integral from a to b, you could say, pi times outer radius squared minus pi times inner radius squared. And then our independent variable here is dx. Another hint with that, if you have a horizontal axis, you are going to be integrating with respect to x. Okay, so then my limits are x equal 1 to x equal 4. The pi that I have in both of those products, I can factor that out all the way out front. And in fact, this came from a multiple choice problem. You would see that all of the answers had pi factored out to the front. My outer radius is x plus 2, and I have to square that. And then my inner radius is 3, and I have to square that. And then I'm integrating with respect to x. So before we finish this problem by doing the integration, something else I want to point out relates to our previous example. We did the same thing there. We just didn't really notice it at the time. We did have an outer radius and an inner radius, and we also had an axis of rotation. You can get the sphere by taking the semicircle that's on the right and rotating it about the x-axis. The x-axis has equation y equals 0. You don't have a washer here because your region is actually connected to the axis of rotation. So you don't have an inner radius. So you would actually say it's 0. The outer radius, again, came from this height, the y value. So really this pi times radius squared that comes from the disk method is just a simplified version of the washer method. Okay, so to finish this example that we left off with, we can factor the pi out to the front of the integral. We can square x plus 2, so x squared plus 4x plus 4, and then we need to subtract 9. So instead of writing 4 minus 9, how about I just write minus 5? Dx. And then antiderivatives of x squared is x cubed over 3. Of 4x is 2x squared. Of 5 is 5x. And then I need to plug in 4 and 1. Pi times 4 cubed is 64 over 3. Plus 2 times 16, so 32, minus 20. And then minus, plugging in the 1, 1/3 plus 2 minus 5. So then distributing my negative, keeping my pi out front, I would have 64/3 minus 1/3, which is 63 over 3. That's the same thing as 21. So let's just write 21. And that means I've already considered the fractions. 32 minus 20 is 12. And then I'll also be subtracting another 2, so that's 10. Plus 5, so that's 15. So we just end up with 36 pi. Here's a new example. Now define capital R as the region bounded by the curves y equal x and y equal x squared. If this region is rotated about the line x equal -1, find the volume of the resulting solid of revolution. Notice here the axis of rotation is x equal to -1. That's different than what we had in the previous example, which was y equal to -1. So you can start to think that maybe we might have a different axis of rotation that would be vertical this time around, so things might be different than what we saw before. So just like we did in earlier examples, let's draw some pictures. So we've got the curves y equal x and y equal x squared, and I am going to have my axis that's to the left, so I'm going to move this over a little bit. So y equal x, that's just a line with y-intercept 1 and slope 1 over 1. And then y equal x squared, just a parabola. So there's our line y equal x, and then our parabola would have vertex at 0, 0, and then it would also have another point at 1, 1. So when you're doing a sketch like this, you might say, oh, okay, they're intersecting, and it looks like I'm getting like a small little region there. So maybe it might make more sense, if you want to zoom in on that, just change your scaling. So I'm going to actually say that 1, 1 is up here. And so my parabola does this, and my line goes in between those 2 points. So this is 1, 1 there. Okay, so our curves are intersecting at those 2 points. So you can see this is going to relate to something that we saw in the previous section. We're probably going to need to find those points of intersection if it's not entirely obvious from our graph. It's obvious from our graph that they are intersecting at 0, 0 and 1, 1. And the region that is bounded is this little sliver right there. So you're going to see some questions like this where you might not be given those points of intersection. You'll have to find those either by graphing really well or just algebraically solving for them. We won't get any other intersection points for this because the red parabola would keep continuing up and to the left, whereas the blue line would continue down and to the left. So I'm not going to draw anything else with this picture, except my axis of rotation. So if my axis of rotation is x equal to -1, then just using the same sort of scaling like I did in my picture, there's my axis of rotation. So now if I rotate my little sliver here on the right around the axis of rotation, you can get a sense of what that would look like just by thinking, well, this point that's on the bottom left, it would have to go out to the left of my axis of rotation and then come back at some point. And then the same thing with this point that's on the top right, but it's going to have to go out a lot further. So something like that. And then I've got kind of like this sliver shape that's taking up the whole image. So it's kind of like the cone shape that we had in the previous example, except I've got this curvature on the outside coming from the parabola. So we again have the same ideas though. Inner radius, outer radius. So if we start with the inner radius, that comes from this blue line and how far it is from the axis of rotation. So now here's the difference between the last example and this one. This inner radius is a horizontal line. The inner radius from the previous example was a vertical line. So now that I've got this vertical axis, I'm going to find my radii by actually subtracting x values. So we can write a note down for that. vertical axis of rotation. Radii, that's the plural of radius, are found by subtracting x values. Which means I need to take an x value for both of these points here and subtract them. And when we do our subtraction, I want you to just remember how we did subtraction way back when we first learned subtraction and negatives didn't exist. It was always the greater number minus the smaller number. So you're going to do right minus left. Just like in the previous example, when I found my radii, I did top minus bottom. So keep that in mind. You are going to take the x value that's on the right and subtract the x value that's on the left. So, how do I get x values for this point that's on the right? That comes from the equation y equal x, which means the exact same thing as x equal y. So any x value for a point that's on the blue line, that's the same thing as y. So I'm going to say for my inner radius, that is x equal to y minus an x value that's on the left. X values that are on the left come from the axis of rotation, which has equation x equal -1. So this gives me y minus -1, which is just the same thing as y plus 1. So see how logically this is the same idea as the previous example, but just since the axis has changed to vertical instead of horizontal, now I'm finding radii using y values, or sorry, y is the independent variable, to get some sort of expression for that. And I'm doing that by just subtracting what x is equal to. So now how about for the outer radius? That's coming from the parabola, because that's furthest from the axis of rotation. So it would be some point out here on the parabola, and the distance it is from the axis of rotation. The parabola has equation y equal x squared. But we can get y's values from that by just taking the square root. Square root of y is equal to x. And notice that that's going to be true for x values that are in this region here, where x is just somewhere between 0 and 1. So the outer radius is just by taking x equal to the square root of y, the x values that are on the parabola, minus the x values that are on the axis of rotation. That's just getting us to really writing this, the square root of y minus -1, which is the same thing as square root of y plus 2. Square root of y plus 1. So now I have my inner radius, y plus 1, and my outer radius, square root of y plus 1. So to find my volume, I'm integrating. My limits of integration now are not x values, but y values. So they're coincidentally the same thing, 0 to 1, but I'm just going to make a note here. These are y values. Because x is going between 0 and 1, but so is also y. That's also going between 0 and 1. And then I have pi times the outer radius squared, square root of y plus 1, quantity squared, minus pi times the inner radius squared, so pi times quantity y plus 1 squared. And I'm integrating now with respect to y. So that's the setup. Once you've gotten to the setup, everything should be a lot easier after this point. You just need to use your algebra skills correctly to get an integrand, use your integration techniques that you've seen to then get your antiderivative, and then just evaluate your antiderivative correctly. So I'm going to factor out pi. I'm going to square the square root of y plus 1, which leaves me with y plus 2 times the square root of y plus 1. And then I have to subtract y plus 1 squared. That's y squared plus 2y plus 1. Make sure you're using parentheses on that subtraction so you don't forget to subtract everything. So if I distribute the negative, then what I have now is pi times the integral from 0 to 1. I'd have a negative y squared. Y minus 2y is a negative y. I'd have plus 2 times the square root of y, and then the 1's actually cancel out. And so then now I can do my antiderivative step. Antiderivative of negative y squared is negative y cubed over 3. Antiderivative of negative y is negative y squared over 2. And then remember that the square root of y is y to the 1/2. So then the antiderivative would be y to the 3/2. And then I have to take the number 2 that was there as a constant, multiply it by the reciprocal of 3/2. So that gives me 4 over 3. And then I need to just plug in 1 first and then 0. So plugging in 1, I get negative 1/3 minus 1/2 plus 4/3. And then plugging in 0, I just get 0 minus 0 plus 0. It's always a good idea just to follow through with that. Don't get into a habit where you maybe see a lot of examples where 0 is just at the end. Just be cautious with that. Try to just be deliberate in plugging in what you have as your limits. So this just becomes pi times negative 1/3 plus 4/3 is 1, and then subtract a half, that's 1/2, so this is just pi over 2. This change in perspective is definitely something that you need to practice to get used to. So let's look at one more example that I've also taken from the homework that is also going to use this concept of integrating with respect to y, so with a vertical axis of rotation. And on this one, we're just going to set up the integral. So the example says, set up the integral that can be used to find the volume of the solid formed by rotating the region bounded by u of y equal to square root of y plus 1 and v of y equal to 2, between the values y equal 1 and y equal 2, about the axis located at x equal 1. Okay, so with this one, they say u of y is equal to the square root of y plus 1. Definitely feel free to do what I would do. I would say that that's x equal to the square root of y plus 1. Again, if we're doing things specifically related to graphs in the coordinate plane, sometimes it's easier to see how just x and y relate to each other. And then v of y, that's just a different function of y. That's all that that means. Equal to 2 means, quite simply, x is equal to 2. Between the values y equal 1 and y equal 2, this is giving you a hint as to what your limits of integration are. And then you are rotating this entire region about the axis located at x equal 1. So the axis of rotation is x equal to 1. So let's do like we did before. Let's draw a picture to start with. So first, square root of y plus 1, let's just plug in a couple of numbers for that. So if y is equal to 0, then x is equal to 1. All right, so that's going to be 1 point on that. I can take another y value, y equal to 1. That would give me an x value of square root of 1, which is 1, plus 1, which is 2. So all I'm doing is just plugging in some numbers for y and getting related values for x equal to square root of y plus 1. There is a restricted domain on this. I can't do any negatives. And if I do one more, if I plug in y equal to 2, then I would get the square root of 2, which is about 1.4, plus 1, so about 2.4. So then putting those in my little graph down here, we said when y is equal to 1, I get an x value of 2. When y is equal to 2, I get an x value of about 2.4. So something like this. What you're really getting is just what sort of looks like a parabola in our, say, y equal x squared sense. But it's really just a square root function that is heading in the positive y direction. So that's x equal to the square root of y plus 1. And then x equal 2, that's just a vertical line. So this is x equal to 2. And then we have the axis of rotation is x equal to 1. So now I've got my curves drawn, my axis of rotation, and now let's take a look at, they told us we want this between the values of y equal 1 and y equal 2, which is telling us that really what we're doing is focusing on this little part right there. So I'm going to remove those lines. So we're just simply focusing on what is almost like a little triangular shape. And then we're going to be rotating that around our axis of rotation, x equal to 1. So you can see we're again going to get some sort of hollow shape to this. We are also going to have an inner radius, which comes from the red line to the axis of rotation, and then an outer radius, which comes from the blue curve to the axis of rotation. So we can write those things down. Outer is just x equal to the square root of y plus 1 minus the x value of x equal 1. That just becomes the square root of y. And then the inner radius, that's just the x value of 2 for the red line minus the x value for the axis of rotation, which is 1. That gives us 1. And so now my volume is integrating from y equal 1 to y equal 2, pi times the outer radius, square root of y, quantity squared, minus pi times the inner radius, 1, quantity squared, dy. And the way that this actually appears as the choice that you can pick from in the problem, this is a multiple choice problem, is the integral from 1 to 2 of pi times square bracket, parentheses square root of y squared minus 1 squared. And then that's it.